One of the most important topics in computing is that of representation, and in this video we're going to have a look at how images are stored inside the computer. So you're probably aware that all types of information are stored as a series of numbers. So text, for example, would be stored as a numerical value which represents an ASCII code or a Unicode value, and things like even programs are stored as numbers which represent particular operations within the arithmetic logic unit, so things like addition, for example. And we've looked previously in the HTML playlist at how colours are stored inside the computer, and that's this page here. In this video I'm going to be using a number of pages from within my website. I'll include the links to those in the description below the video. So how the images in this example are stored is as bitmaps. And what a bitmap is a series of pixels, a series of coloured, usually rectangles, representing the image. Sometimes you can see those if you lean in close to your monitor or your television. Each of them will have a particular colour, or a unique colour, and a separate colour with a discrete colour within the image, and that's stored as a number, or in this case 3 numbers. This is a common way of doing it, storing the amount of red, green and blue in each of the pixels, and it's usually stored as a value between 0 and 255. So the background colour of the rectangle at the bottom is the colour we're representing at the moment. So it behaves like light. So if we've got nothing, we get black, and then if we turn them all full up, we get white. And if we have the same amount of each, we get a shade of grey. And sometimes it's obvious how to make a particular colour. So for example, if we want purple, we'd have some red and some blue, but not always. And sometimes you can use the idea of complementary colours. So if you think about the colour wheel, which is a bit like a rainbow going around in a full circle, complementary colour is a colour on the opposite side of the colour wheel from the number you're thinking about. So for example, it's not obvious how you make something more yellow by combining red, green and blue. So to make something more yellow, you look on the colour wheel, yellow and blue are on opposite sides. So if you make something less blue, you make it more yellow. So that's just a recap of how kind of colours work. And so effectively a bitmap is stored as a series of numbers representing the colours for each of the pixels. So why is it useful to know that? Well, if we have a look at this page here, what this page does is it allows you to upload an image. So I'm going to pick an image. So these are pictures from my OI Computer Scientist folder, which I'll also include a link to. It's a bit of a game, and it's about recognising famous computer scientists. It was inspired by the children's book Oi Dog and also Elf on the Shelf at Christmas time. And the idea is the computer scientist is resting upon a thing that rhymes with their name. So like Oi Cat, sit on the mat. This is Windsurf on some turf. So if I open that, the first thing it does is it does the processing on the client side. So there might be a short delay, particularly if it's a big image, before the image appears, and it'll tell you how many pixels it's using to represent it. So it scales it down just for demonstration purposes. So there's Vint there. So if we zoom out just a little bit so you can see the sliders at the bottom, I've added some sliders at the bottom so you can manipulate the image. So why is it useful to know that the image is stored as numbers? Well, if you didn't know how an image was stored and you wanted to understand how PaintShop worked, or you wanted to write a program to manipulate those images yourself, it would all seem a bit mysterious, wouldn't it? It would all seem a bit magical. But knowing that an image is stored as a series of numbers makes us think, well, hang on, what about if we add to those numbers? Or what about if we multiply those numbers? What would happen? Well, a second ago, we looked at the idea that if you increased the numbers representing the colours, so if you added more red, more green and more blue, the image got brighter. So that's what the top slider does. It adds to all of the numbers representing the image. So if we increase all of those numbers, what happens to our image? Well, it gets brighter. And if I reduce, so in the middle is 0. So if we go to the left, we're subtracting. If we subtract, it gets darker, and we can see how much we're subtracting. So by default, it subtracts on all the channels, red, the green and the blue. We can just select one colour channel if we want to. So we can turn up the green, for example. And we can also see that complementary colour idea here. So if I turn down the green, we can see that it gets more magenta, because magenta's the complementary colour of green. And you can do it in a combination of colours. So if you make it red and blue, for example, it kind of gets more purpley. And also we can, because I had this idea thinking about the numbers and how it is represented. I'm a member of a photographic club, and quite often my fellow members like their black and white photography. And I was thinking, well, how does black and white conversion work? Because all cameras these days take colour images. Is it as easy as just finding the mean average of the red, the green, and the blue? And yes, it is. So that's all that does. It represents, it averages out the red, the green, and the blue, and we can see a black and white version of the image. And exactly the same thing happens. If we increase the values, it gets lighter, and decrease the values, it gets darker. And we can also, let's just go back to the colour version. So that's adding. What about if we multiply? Well, if you think about what happens when you multiply, so for example, if you had numbers from 0 to 255, if you had a dark colour, so if you had 1 and you multiply by 10, 1 becomes 10. And usually we think of scaling in terms of multiplication, but effectively that's added 9 to it, isn't it? If we do the same with a bigger number, so if we take 100 and multiply it by 10, then it goes up to 1,000. So that's got 900 times bigger. So the impact of multiplying bigger numbers is larger. And so if you think about what that would do to the colours, if we turn that up, we can see straight away probably it's increased the contrast, isn't it? Because it's increased the difference between the light and the dark. What the threshold does is it changes the point about which they're multiplied. So if you so we've selected 105 there. So basically what that would do is it would multiply the difference between the colour or the colour value and 105. So basically those below 105 will get smaller and those above 105 will get bigger. And that just changes the range of the expansion, if you like. And we can combine the two. So if you decide that increasing the contrast has made your image too bright, we can just darken it down a bit using the top slider. That also works on the grayscale as well. In fact, in some ways it works a bit better on the grayscale because contrasty colour images look a bit odd. And then finally, at the bottom, we can also adjust the number of bits used to represent each of the pixels. So you might be familiar with the idea, of the range of numbers that you can represent in a certain number of pixels. So in n pixels, we can represent 2 to the power of n values. So 3 pixels, for example, 2 to the power of 3 is 8 different values. So that also has an impact on the size of the file, doesn't it? So there's a separate playlist on calculating file sizes, but what you would do to calculate the size of this file, you would multiply the height and the width and then multiply that by the number of bits representing each pixel, and that will give you the total number of bits altogether. So I'm just going to put these back to the middle to turn Vint back to normal. So to begin with, we have 8 bits, 256 values for each colour channel, or just 256 values altogether in the case of the grayscale. So what's going to happen if I reduce the number of bits? So it's going to make the file smaller. That's quite a common GCSE question. But what's it going to do to the image? So if I turn it down, so that's 8 bits. Keep an eye on Vint's his forehead particularly. That's where you start to notice it first, I think. So 7 bits, don't really notice much difference. 6 bits, still looking okay. Slight speckly effect on his head there, but it's looking okay. 4 bits, we can definitely see he's got a bit of kind of speckling on his head there. But it's still not looking too bad. So effectively we've halved the size of the file there, and he's still looking okay. So that's quite a good way to reduce file size. But if we go any further than that, he's starting to look a bit odd, isn't he? And you get down to a certain point. So we've only got 4 different shades of grey there. We've got the black, we've got the white, and then 2 shades of grey in between. And notice if we go down to 1, it's literally black or white. So that 1 bit can have 2 values. It can be black or white. Where the threshold will be in that particular case will obviously vary depending on the other settings as well. So you can use all these things in kind of combination. You can adjust the contrast and so on. If that was the effect you wanted, and if you were making him out of Lego or something, that might be quite a desirable effect. You can also do it in colour, and in fact, in some ways, you get a more interesting effect if you do it in colour, because, well, you'll see in a minute. So 256 values now for each channel. So 256 values of red, 256 for green, and 256 for blue. That's a total number of combinations. 256 cubed is about 16.8 million. And again, if we reduce that, we can reduce the size of the file and see the impact on the colour information there. So linking this into other areas of the curriculum, if you think about perceptual coding, so that's lossy compression, it tries to throw away or discard information that it thinks you're not going to notice. So in reducing, from 8 down to 6 bits, we don't really notice much of a difference there, do we? But it's probably, it's quite a reasonable decrease in the file size. So we keep going, and again, we probably don't really notice until we get down to about there. So 16 colours each for, so that's still looking okay. And then we go a bit further, it does start to go a bit strange. So look at his head again, it looks like he's made of spam a bit there. So, and we keep going. And now there's only 64 colours altogether, 4 shades basically for each of red, green and blue, and then it gets even worse the lower we go. So there's only two levels for each colour, and again we can tweak that, so we can adjust it slightly. But we can see that that's a bit too much really, unless we particularly wanted that effect. But a photographer might describe that as solarization, for example. That might be a desirable effect. So what we've looked at here is how some of the things that you might want to do in a simple image editor, if you're just tweaking your photos, if they're a bit light or a bit dark, or you want to do it, increase the contrast, how you could do that just with a bit of simple arithmetic. The other thing you might want to consider, particularly for the GCSE, is whether the information about those pixels, so we've got 600 rows, no we haven't, we've got 480 rows of 600, so it's 600 wide, 480 tall. So that's thousands of pixels. Is that enough for us to be able to reproduce? If we've got those thousands of numbers representing the colours, is that enough for us to be able to put that image back together? Well, we've got another page that helps us to investigate that. So I'm going to pick a different image this time. So this is Ada Lovelace on a suitcase. I'm going to upload that. And again, a bit of client-side processing, so you get a slight delay. It tells you how many pixels there are, but what this page does is it ignores the sizing information. So it ignores how wide and how tall the information is. So if we just only in our file had the colours of those 32,370 pixels, could we see what the image was about? Well, as you can see, can't really recognise that image there. So what the slider allows us to do here is to adjust the aspect ratio, the height and the width of the displayed image, and to see the effect. So at the moment, so to begin with, it tries to make it about as square as is possible. So this is 181 by 178. We can see that's not right, so we could try making it wider. So all we're doing there is we're arranging the pixels differently to try and make the image. So now it's 221 by 146. What that means is we start a new row every 221 pixels. What we notice as we do that is occasionally we get things that look a bit like a possible image. But if you think about what that would mean, so there, for example, if you start a new row only half as often as you should do, effectively what you're going to get is two images next to each other containing every other row, if that makes sense. The reason this image gets smaller as you get wider is because if it's too wide to fit in the box, basically it halves the size of the pixels. So once you get to about this point, it will suddenly double in size, so it fills the box better. So at some point, obviously, we'll get the right arrangement, and you'll be able to see what the image is. And if we go left of that, then obviously we get the same issue. Occasionally we get sort of things that look a bit like a possible image, but they're not. So that's just a quick look at why it's useful to know that images are stored using a series of numbers, and also the idea of this is metadata, the idea that we need a bit more information than just the colours to be able to reconstruct that image properly. So real cameras, for example, or phones or image manipulation software will store extra information in there as well as the dimensions. So you'll get things like the number of colours that you use, possibly compression techniques. In cameras, you get things like aperture, shutter speed, whether the flash fired. You also get GPS coordinates of where you took the photo, so you don't have to remember exactly where you were at the time. Things like that. If you're interested, you can do some of these things in Python. So there are links at the bottom of this page and the bottom of the previous one so that you can copy the data from the file that you've uploaded just as a series of red, green and blue values. And there's a link on the previous page to a Python project in Replit which you can use.